Hello, everyone. Today, I want to talk about benchmarking, the library that allows to reliably measure app performance. And my goal for this presentation is not just to show you some basic facts that you can easily find in the documentation anyway, but rather show you this tool from a more practical perspective and share what were my experiences with it. But first, let me share with you some interesting but seemingly not connected fact. You probably all know that most car companies test the efficiency of their car in reduced scale wind tunnels. Using those small scale models make development process much more efficient and cheaper than testing the full-sized car. But had you known that one company uses for their test models that are made of clay? At first that seemed to me very odd, but then I realized that it actually makes a lot of sense. Why? Well, because clay is very easy to shape. So using clay models allows them to make quick on-the-spot changes and immediately test how those changes affected car efficiency. And that way, they are able to make even 15 changes in one shift. So gather 15 data points. And this is a huge amount of data that helps increase efficiency of their fleet. And when we talk about car performance, it's pretty obvious that testing performance before creating full-size working car or even testing on clay models, it makes a lot of sense. Making experiments and learning from obtained data about performance at a very early stage of development, it's crucial to create a great product. But when we think about app performance, well, then it doesn't seem that obvious. And as it turns out, we very rarely work that way. Very often, we find out about major performance problems in our apps just before app is released during regression tests, or even worse, when the app is already shipped and when we see comments from dissatisfied users. And at this stage, fixing performance problems is much more expensive. Why? Well, it's much harder to find the cause of the problems when we wrote the code a very long time ago. Also, the changes that we introduce at that stage are much more invasive. And if we are not very careful, we may even break some crucial features of the app. And in this presentation, I want to show you how benchmarks can allow us to change that. How they can be as those clay models, which allow to easily experiment and enhance app performance, while we are still writing the new features. But to help me show you it on some practical example, I created some demo app. The app is fairly simple. It consists only of one screen with the list of mock shoe offers. This list was created using Recycler View, of course, and it has 4 different item types, so also 4 different adapters. To display some offers vertically, some of them are horizontal, and some of them are in nested scrollable lists or a view pager. But as I said, the app is pretty simple, and there are very few lines of code here. But I still managed to add some mistakes to this code. This mistakes doesn't necessarily break the app, but they decrease its performance and make scrolling of this list not smooth. And we can see it clearly in Profile GPU rendering tool. This tool is available in the developer options, and it works on any app that you have installed on your phone. And as you launch it, it creates an overlay layer with a scrolling histogram, a visual representation of how much time it takes to render the frames of a UI window. So these colored vertical lines show how much time it takes to render one frame. The green horizontal line, I will make it a little bit bigger so you can see it better. This line is 16 millisecond limit. So as you can see, many frames take much more than 60 milliseconds to render. And why 60 millisecond limit is so important? It's because it relates to 60 frames per second, so the frame rate which is used in our phones. And when we cannot fit in that 60 millisecond limit, some frames are dropped and animation is not fluid for our users. Okay, so we have our buggy demo app, And now let's see what's wrong with it. And to do it, we usually use the profiler. And the profiler is a tool that probably most of you know and use, and it's great. It's a great tool to look for a source of performance problems. It's embedded in Android Studio, and it requires no setup at all, so we don't have to modify our code to use it. So using Profiler, I can easily record all methods that happen while I scroll the demo app, and then look for some suspicious code that is making it slow. So let's check this out. So here we can see a graph that shows recorded method calls from the demo app. I zoomed this graph to a moment when binding was happening. And why binding? Because when we have an app with bad scroll performance, it usually means that some long-running operation is happening when binding the data to the view. So it's usually the best to start optimizing here. Okay, so by looking at this graph, we can see that bind takes over 10 milliseconds, as Profiler says. So it's definitely too long. And now we can look for some suspicious calls. And here you can see the first mistake that I planted. Here is some number format instance created that takes about 1.5 milliseconds. So let's look at the code to all see what we can do about it. Okay, so as you can see, there is indeed a problem. Each time format price is called, the new number format instance is created, and it's definitely not needed. We can easily optimize it by just moving it moving this piece of code to some value. So that way, the number format is only created once when the formatted is created, not on every bind call. Okay, so that was the quick fix. Let's go back to the graph once more. And here we can spot another long-running method, setTextAppearance. And by looking at the graph, we can see that it took over 5 milliseconds. Okay, so let's look at the code once more. And here you can see that I set text appearance on every bind call. And because it takes a lot of time, we should optimize it. And we can do it very easily by just moving setting text appearance to XML. So performing these operations only once when the view is created. Okay, so after doing those two easy optimizations, I recorded method calls once more and zoom it to bind. And you can see there is no more suspicious code that we can optimize, and binding takes now about 7.5 milliseconds. Previously, it was 10 milliseconds. We might have expected a better result since the methods we optimized took both 6 milliseconds, but I will explain why those numbers doesn't end up in a moment. Okay, so why have I shown this example to you? I show it so we could all analyze the process and think what was wrong with it and what could be, well, optimized. This process consisted of 3 parts. Measuring code performance using Profiler, then we looked for suspicious code, and then we changed something to see if it will allow to improve app performance. Okay, so let's focus on measuring phase for a moment. Profiler is a great tool. I'm a huge fan of it, and I use it a lot, and I think we all should. But as everything, it has some drawbacks, and those drawbacks can disturb our work sometimes. And the first most obvious problem is long iterations. Each time we want to measure how our changes impacted app performance, we have to build and run our app, open Profiler, record all methods, and then manually interact with an app. Then stop the recording and wait for the results to parse. And then finally we can find in the graph the method that we want to optimize, and we can check the result. It might not be that bad if we do it once in a while, but this long feedback loop can be really annoying, especially when we experiment with some piece of code and want to quickly see if it worked. Okay, so that was the first problem. The second problem might be a little less obvious, and this is the measurement inaccuracy. The results that you observe in Profiler are not very accurate. Why? There are a few reasons. The first reason is connected with CPU profiling mode that you choose. We usually use sample Java method or trace Java method mode, so I will focus on those two. In sample Java method mode, profiler captures call stack at some interval. And this interval is, of course, very frequent, but it can add some error to our measurements. And we can even miss some shorter method calls because of that. That interval and the fact that profiler adds some overhead while measuring our app, that all means that the same method called with even the same parameters, even on the same recording, this method may take different amount of time. And here we can see some example. The method that I measured on the same recording took once it was less than 25 milliseconds, once it was 26.8 milliseconds, and once even 30 milliseconds. So this is a really significant difference. Okay, so maybe the solution is to use trace Java method mode when we want more accurate results. This mode is known to be better for tracking even methods with very short life cycles. Well, not really. Trace Java method mode adds a huge overhead, and it highly impacts runtime performance. And it, of course, influences profiling data. So the same method that in sample mode took 29 milliseconds, in trace mode may took almost 200 milliseconds. And both modes are obviously great when we are just looking for some performance hotspots to decide where to focus optimization effort. But it's good to be aware that they are not giving exact and easy to compare results. Okay, so there's also another problem, and that's that the profiling your app requires it to be in debug mode. The code that your users see in release mode is very different to app in debug mode. Runtime does very little optimization to your code when it's in debug mode, so the results that you see in profiler may be much higher than in release. And it wouldn't be that bad if the error was systematic, but it's not. Here's a graph from the article Busting Android Performance Myths. This graph shows the benchmark duration of some method calls recorded for debuggable true or false. And as you can see, for some methods, being in debug mode added almost no overhead at all. But for some, the measured value increased by even 50 or even more %. So when you want to measure your code with good accuracy, using profiler might not be the best option. And there is also another problem with profiler, and it relates to the second phase, so finding out what is wrong. This phase cannot be automated using this tool. Profiler is fully manual, so it's not possible for it to automatically detect performance problems and notify us when it happens. It's simply not the purpose of this tool. But there is another solution that can give us more reliable results and help us to find performance problems automatically. And this is Jetpack Benchmark Library. This library allows us to write automated tests which measure the code performance. It was released, I think, about a year ago, but it was used in Google internally for quite some time, so it should be pretty stable. The API is fairly simple. We have to, of course, integrate the library, but I will omit this step to not make this presentation even longer. You can easily find all the information on how to do it in the documentation. But after we integrate this library to our project, all we have to do to create new benchmark is just to add new test class as we would do it for regular UI tests. And then in this test, just define benchmark rule and in block measure repeated, we can write a code that should be measured. We can also use block run with timing disabled when we want to write a code that should be run on each iteration, but not added to measured result. And it's usually used for some initialization. And that's it. As I believe it's the whole benchmark API. It's pretty simple at the surface, but there's a lot under the hood to make benchmark results as stable and reliable as possible. When we run this test, the benchmark runner will run the code specified in measuring repeated block. We'll run it multiple times, and the amount of iterations can vary. Sometimes it's several dozen, sometimes a couple hundreds, or even thousands. And in each iteration, library calculates an error and stop measurements only when measurement certainty of this result is fairly low. Benchmark runner also handles warm-up. It stabilizes clock for a time of a whole test, and even detects if the test configuration is correct. So it checks if we are running the test on physical device, because we shouldn't run benchmarks on emulator. It checks if our device has enough battery, and it also checks if we are not using debug mode, because as we said earlier, that can skew our results. All that means that achieved results are much more reliable than if we were just measuring similar code in the profiler, or just writing that test using simple for loop and measuring this time on foot. Okay, so let's go back to the process that we analyzed, how it can be improved by benchmarks. If we use benchmarks in measuring phase, it will give us much quicker iterations and more consistent results. That means that we can experiment much more quickly and with greater confidence know when our changes are indeed increasing performance. But what's for me even more exciting, if we integrate benchmarks with the CI, we can use those tests to automatically detect performance regressions. So find out about possible problems much more quickly. Okay, but enough talking. Let's finally see some code. I will show you how to create a benchmark to measure scroll performance in the demo app that you saw at the beginning. So as I said, the app consisted of 4 different item types. And we cannot test this list in this form because it would be impossible to interpret the results. Rendering some item types can be slower than the others. So for each item type, we have to create separate benchmark. And that way we'll be able to interpret the results to know which adapter was slow. Okay, so let's take one of the item types and write a scroll benchmark for it. For the others, the code will be pretty similar. We start with an empty benchmark test that I showed you earlier. This time we need also some activity test rule that will launch some activity created for this test. This activity only contains the recycler view with adapter that we can feed with data. In this test, we also need to do some setup in before block. So here's the setup block and what we have to do with it. First, we need, of course, put some data to the adapter. And here's the first thing that you should remember while writing this kind of benchmarks. The thing is that we need a very long list of items to test the scrolling of this list. As I mentioned earlier, benchmark runner will run our scroll test many times, as long as it needs to achieve results with a very small measurement error. And because of that, it's really important to initialize adapter with a lot of data, so the list to scroll won't end during tests. Because if we run out of items during tests, that could lead to achieving unrealistically good results, because app just won't be able to scroll and we will be measuring nothing. The amount of items that you should put on this list can be arbitrary, like I'm shown here, but then you have to, this list have to be very long. And it's good to check beforehand how long it needs to be, and then make it even longer than we think it needs to be, just to be extra safe. An alternative can be to create a list where items are created on demand by overloading get method. That way, it's not possible to run out of items while scrolling, so it's a much safer approach. But we have to be aware that time it takes to create one item is added to test result. But it don't have to be a problem, since this is usually a very quick operation and doesn't change in time. Okay, so that was the first thing in the setup. Another very important thing is to create items with data that is as random as possible to avoid caching views. And caching view can also increase achieved result artificially. So in this test, I cannot use the pre-mock data that I showed you earlier. I have to create a data set with some random strings injected just to get proper results. And the third thing is to decrease recycler view height and setting it to 1 pixel. And this step is advised in benchmark samples to avoid creating a lot of items at once. But in my experience, it had very little impact on the measurements. So I don't think it's really that necessary to do it in that case. But it won't hurt. As I measured it, the measurement error was a little lower when I added these two lines, but it wasn't a significant difference. But it might be only in my case. Okay, and lastly, all this code has to be run on the UI thread because it's touching the views. So that was on setup. Now let's look at the benchmark itself. And writing this benchmark is pretty simple. All we have to do is just to get the recycler view from activity rule, and then in measure repeated block, just scroll a list by the height of one item in each measurement iteration. And this scroll by is just, of course, method available in the recycler view. It's not just, it just scrolls a list by height of one item. And also this test should be run on UI thread. Okay, so that was all test, and what that test measures. This benchmark measures how long it takes to detach previous element, attach the new one, layout it, and bind it. The time it takes to create view is not measured in this test, since recycler view reuses views. Okay, so what were the results? Before all the optimizations that we made at the beginning of this presentation, scrolling by height of one item took about 3 milliseconds. After ensuring number format is not created in each bind, that time dropped to less than 2.5 milliseconds. And after moving setting text appearance to XML, the time it takes to scroll one item drops to a little over 1 milliseconds. That means that all those changes allowed us to achieve 62% better scroll performance. And in this, it's also worth mentioning that the number itself, the number that we see in benchmark, it's not necessarily exact. The results might be a little bit higher than the ones that we see in production, that our users see. And that's okay, because all we care about is the difference that our changes cause, and that difference is reliable. Okay, so but you can argue with me that it's not worth to write benchmarks for this case, because we were able to achieve those results even without benchmarking. We found those issues in Profiler after all. But there are some cases when there is really hard to spot a cause of inefficiency in Profiler. But thanks to benchmarks, it becomes as clear as day that there is an inefficiency when we play with this code a little. And it's really easy to come up with the cause of this inefficiency. Like in this example. This is a class, this class is a view holder of swipeable item. It consists only of viewPager2 that is initialized by setting off-screen page limit to 1. As it turns out, this code has some bug in it. And this bug is not crashing the app, but is making scrolling much slower than it could be. And what can be wrong with it? I will drink for a second so we can think about it. Okay, so the problem lies in setting the off-screen limit. Off-screen page limit allows to specify how many pages are rendered on each side of the page that is currently visible in the view pager. And that way, when the user swipes to the next page, he or she sees the content immediately. And for the view pager 1, this code would be correct. Off-screen page limit is even set to 1 by default. But as you can see, I'm using viewpager 2. And viewpager 2 is much different than the previous viewpager because it was written on top of recycler view. So it uses all mechanisms and all optimizations that are available in recycler view. And one of these optimizations is prefetching. And prefetching allows viewpager to render much more quickly because it renders only the page that is currently visible, and the remaining pages are loaded also, of course, on the UI thread, but after some brief amount of time when UI thread is already free. And that way, this operation doesn't block this thread and allows to much quickly render viewpager. And as I learned from playing with benchmarks, setting off-screen page limit to 1 disables this mechanism and replaces it with the less optimal behavior that we know from previous viewpager. And this mistake would be very hard to spot in Profiler. It's not impossible, but you really have to know where to look. But it's immediately visible when we see benchmark results. With off-screen page limit set to 1, scroll of one item took over 11 milliseconds. And after removing just this one line, so when viewpager uses prefetching, it takes only 6 milliseconds. So that's 48% improvement. But the number itself is not that important. What's more important is that by using benchmarks, we can see clearly how this change affected performance. And also, if we write some scripts, we can even detect automatically when someone introduces that kind of performance problems to our code base. But to do that, we need a CI integration. And I think the ability to integrate benchmarks with CI is the biggest selling point of benchmarks. However, there are a few things that we have to take into consideration while creating the scripts that are using benchmarks. And the first thing is how to interpret the results. In case of unit or UI tests, it's really easy to interpret the results. Tests can either pass or fail or be skipped, so we can just fail CI build when some test failed, and that's it. But in case of benchmarks, the results that we get are just numbers. And those numbers are not possible to interpret without comparing it to some other number. For example, the result from previous build or from master branch. And benchmark library, besides printing test results in console, also allows to retrieve full benchmark report with all results in JSON files. So we can parse that file in scripts and then process it. And the file looks like this, and it contains a lot of information. So, minimum and maximum results, median, the results from each run, etc. And how to interpret and show the data. The simplest solution might seem to be just to put it on the graph, so we can look at it and see on each build if performance changed. And it's feasible when we have very few tests, but in time, after we add some more benchmarks, those results may start to be unreadable and almost impossible to interpret. So we also need to write some logic that will interpret the data for us. And one approach might be just to compare the result with the result from the previous build. But this approach is not perfect. And first problem is how to determine how big the difference must be to...
We want Marco's going to do a question. How much do we want to stay?
Sorry, the audio just. First problem is how to determine how big the difference must be to classify it as a regression. And it's especially hard because for some tests, especially the ones that measure UI performance, something that for 2 data points looks like a regression, when we look at more data points, it often turns out to be just noise. And some benchmarks are more stable, and some, usually the ones that are connected with UI performance, are less stable. So we need some solution that will allow us to filter out this noise. And the better approach may be to analyze the data, more data points, as is done at Google, and to use step fit function. This allows to filter out some noise. And the function works in a way that it calculates average result from a couple of builds before change and the same amount of builds after change. And if the difference is higher than the standard deviation, the algorithm marks this change as a possible source of performance regression. And we see how it's done at Google, it's done like that at Google in their public benchmarks panel. And here you can see that if an algorithm finds a change that caused the average result from 5 builds before and after the change differs significantly, it triggers the alarm. And this alarm has to be handled manually. So someone has to manually confirm it's an issue and create a new task to fix that issue. And why it's manual? Because sometimes performance regression is something that is expected while we are adding new features. So it's not always the bad thing. The panel that contains results from benchmarks created at Google, as I said, is public and it's available at this address. And normally I would move to live demo and click at the panel while talking, but I don't trust my internet connection that much, and we also have very little time, so allow me to show it to you on some recording and screenshots that I prepared a few days ago. So when you open the address that I showed you on the previous slide, first thing you see is almost blank page with a menu on the left and the query button. And when we click this button, we can see a dialog with the list of benchmark tests. And here are, I guess, all the tests on all the benchmark tests that are written in Google. And I just searched for one of them and selected it. And as you can see, there are 18 matches here now, and I can plot it, but I will do it in a second when I select more options. Okay, so then I selected sub-result, and here you can see are some also sub-results that I can select to plot. And I can even select the device name, but there are very few options here. And there is also option to select SDK release name. So we can see how benchmark results vary depending of SDK release name, SDK version. And here you can see the graph, and I can click on it just to see which is which. And as you can see, even after I told you how reliable benchmarks are, there are some irregularities. So it's good to have some filtering algorithm to detect regressions in that case. So here is this graph for this benchmark. And we can also add a different benchmark using query button, and I will do it now. And here, after I click this button, I can select next test and plot it on the same graph just to see if there is maybe any correlation between the results of these two tests. And here you can see all see it. Okay, so that was that were benchmark results, but I think the thing that I really wanted to show you are alerts and triage. And first, let's see alerts tab. And in this tab, you can see how they configured automatic alarms when benchmark results change. And there are two configurations for two different devices, but let's focus on the first one. And here you can see that they are using mean value and some specific device. But I was looking for some more specific information and on how this alert is configured. And I cannot, of course, click edit because I don't have sufficient rights. I don't work at Google. But I and we all can click dry run. And here you can see more information about this alert. And as you can see, they are using step feed function with the radius of 5 and some other options. And even when you and also when you click at this this box, if you are really nosy like me, you can see a dialog with even more options and some descriptions. And I won't go into details on all of it, but if you are interested in this topic, I highly encourage you to check this out. There are many interesting things here. Okay, so another screen that I wanted to show you is triage tab. And here you can see all commits that triggered the alarm. So to see more commits, that the list of commits that I have here, you have to select the right filters the filters that I selected here. So that we want to display regressions and alerts from category runtime, because there are also alerts from build time here normally. And here we can see that there are some alarms connected to some specific commits, and they are not yet resolved since they have some question marks, these question mark symbols on them. But as we scroll for a bit, you can see that some of them were marked with check and some with the cross mark. And as we click off one of the crosses, we can find similar dialog that I showed you earlier. And this dialog shows which benchmark was affected and how results looked like. And someone marked it as something that should be fixed and assigned an issue for it. And here you can also see view on the dashboard button. And this button leads to the screen with the full graph for this benchmark. And I think this view might be helpful to see the results in the longer time frame to determine if this alarm is indeed a problem and not just some random flakiness. Okay, so that was one of the cases. The next scenario that happens sometimes is when alarm is triggered by performance improvement. And as you can see, even in this case, it's possible to mark that as an issue that should be fixed. And why? And that's because sometimes unexpected performance improvement may also be a bad thing, because it can, for example, mean that we just removed some feature that shouldn't be removed, and that's why the code got faster. And maybe that was the case here. And of course, sometimes performance improvement or even performance regression is something expected as we write a new code. And in this case, the check is selected, and I guess the ID of an issue that caused it. And the last very, very common situation is when alert was just triggered because of some random irregularity in the test results. And here you can see that the situation that looks like a regression for 10 results, when we look at the dashboard, it turns out to be just noise. And for such a large benchmark set that they have at Google, it's inevitable, even when using step feed function, that they get some false positives. Okay, so that was the platform created at Google. I really encourage you to check it out by yourself, and maybe it will inspire you to write something for your project. And it definitely inspired me. I wanted to implement something similar, of course, for a smaller scale, at work in Allegro. But I wanted to approach it a little bit differently because we had different needs. I wanted to create a configuration in which, before any branch is merged to master, we not only require the code to be reviewed and approved, of course, and to run a build, but also to run benchmark tests to get a confirmation that the changes we want to merge doesn't cause any performance regression for the critical paths. To do it, I, of course, created some benchmarks, but I also needed a bunch of scripts to integrate them with the CI and stash. And those scripts, some written in Shell, some in Python, were used to run our benchmarks, to parse the results, to compare results with the ones that were reported at master, and to send the report to stash in the form of a PR command. And the command looks like this. As you can see, the report contains results from all benchmarks, well, all 3 of them, and highlights when there are any regressions or performance improvements. The solution that I created is, of course, much simpler than the sophisticated system that they have at Google. And of course, it's not so powerful and versatile, but it has an advantage that we needed, a quick feedback loop, so that if there's any regression, it's paths that are really critical for us, we know about it before merging the branch. And of course, this solution has some drawbacks. As you can see, I only compared 2 data points, even after I specifically said that you shouldn't. So, we do sometimes encounter false positives because of that. Also, I noticed running those benchmarks is relatively slow. And for those 3 benchmarks, it's not really a problem, but if we had that many benchmarks that they have at Google, I think it wouldn't be feasible to run all benchmarks before merge. It would very slow down our work. But all in all, I think benchmarking library is very interesting tool, and I had a lot of fun playing with it. And just to quickly sum up, as I show you, benchmarks allow us to easily experiment. The results are much more reliable than the ones we see in Profiler, and we can also iterate much more quickly. Benchmarks also allow us to write UI performance tests, so we are also able to measure things like scrolling, as I showed you on an example. And of course, as everything, they have some drawbacks. It takes a lot of time to write and configure benchmarks, especially if we want to run them on the CI. We don't have that problem with the Profiler, but I think those 2 tools are both serving different purposes, and we shouldn't benchmark everything, only the code that is frequently run and really critical for our app. All in all, I think it's definitely worth trying using benchmarks, especially because it allows us to automatically detect performance regressions before shipping the app to the users. And I think it can really be weight off our shoulders when we are releasing the app. Okay, so that's it. Thank you very much. If you have any questions, I will be more than happy to answer them.